Okay. Hello, everyone. Welcome to my talk about Memory Profiler 1.1 and how you can use it to improve performance of your application. Well, a little bit about myself. I am Anton Kruglyakov, senior software developer, profiler team in Unity. My primary field of work, all the low-level stuff in Unity Profiler and Memory Profiler. And that's why advanced warning. This talk would be quite a lot about low-level stuff. How memory works on the operation system was quite a lot of theory. So no video, no audio, no funny stuff, just boring black text. So let me tell you a bit about what this talk is going to cover. I will start with overview, a short introduction of what we will look at, what this talk will cover, what's not. The next topic will be resident memory. It's a new addition to Memory Profiler 1.1. I will show you why we added it and what it is useful for. And the last will be about, we'll analyze memory snapshot by looking at each category in it, and we will talk about all of them in the context of new available information about resident memory. And the last one will be about untracked category. I want to dig into what is untracked, what usually hides there, and how you can analyze it. So my goal by the end of this talk is just for us together to understand what Memory Profiler shows you, understanding what are allocations, what's your in physical memory, why new resident memory was added, and what it gives you, and how all of that affects your application memory footprint and performance. Question to the audience. How many of you use Memory Profiler? Could you please raise your hand? Oh my God, okay. Well, I mean, it makes us happy. It means you use our tools, which is nice. So let's begin. So I will start with the overview. For this talk, I've made a snapshot, which I'm going to use through all my slides. And it was taken from Android game. And obviously, because it was taken on Android game, it has Android bits. But apart from this small section, which is Android specific, all the rest are universal and applies to any platform. I'm not going to cover manage/garbage collected memory much, as this topic is well covered. I think we have quite a lot of YouTube videos, tutorials, documentation, and blog posts about that. So there will be a link at the end of the presentation, but this talk will be more focused on low-level stuff, and the talk is kind of less about what you allocate directly and more about what is being allocated for you. Because Unity operation system and third-party libraries could allocate. And yes, that's what we're going to focus on. Also, it's about allocations which might look scary in some review, but in reality might not be what is actually affecting your memory footprint or application performance. We'll talk a bit about how operation system manage memory, so that would be theoretical part, and why some big allocations can be ignored or not as scary as they look like. And before we dig into the captured memory snapshot, as I mentioned, we need to spend some time on theory, and the theory would be mostly about two particular terms. Through this talk, I will be using term allocated and resident. We had kind of a set of updates through Memory Profiler where we changed what terms we have used because we used committed, and now we realized it kind of not what we actually showing. So the latest profile, it used specifically two terms, allocated and resident. And I want to make sure that we're on the same page what they actually means. So in simple terms, allocated just how much memory has been requested. And when you request it, operation system like makes a promise that it will be able to provide you that memory. It does so by committing physical resources, like system memory or space on disk. Many platforms, for that reason, because operation system needs to commit resources, call this memory committed, well, specifically on Windows. Well, if for some reason the operation system doesn't have enough resources to commit, you will get out of memory. Here, like as always, we have multiple platforms. Well, I have to make a note because it's not actually completely true on Linux, because Linux allows you to overcommit, but we will get to that later. And the next big thing is resident. Resident is, well, strictly speaking, is what is actually currently present in your physical memory. And not all allocated memory is actually resident. And that could be for quite a lot of reasons. And they are, well, the memory just could be empty. So you or somebody allocated memory but never used it. Operation systems are quite clever, so they just know how to mark this kind of memory, like regions, as empty, and they don't contribute to your application memory consumption because they are never present in actual physical memory. Well, the second biggest, well, the most common reason, it hasn't been accessed for a long time. This is much more platform dependent because it can be moved to a secondary storage like swap file, and this is commonly can be found on desktop platforms. But as well, it could be in compressed memory, which is desktop and mobiles as well, because on iOS you have compressed memory. And the last most important reason would be if for some reason the operation system needs physical memory right now for something else, and that something else is actually more important for operation system than your application. Most likely, if that happens, you're probably already running low on memory because operation system needs to start like juggling what it can load and unload. As well as like, why is it important is that as soon, like even before you get to that, you actually start experiencing performance regressions. Because in modern operation system, there is no such thing as free memory. All the memory which is free, mostly used for different caches and, well, caches. Even if it's like not about caches, you have map files which are being made resident because you accessed them, and well, they've been discarded, so after that they need to be reloaded again, and any access to secondary storage is pretty slow. I will going to cover that in more detail when we get to executables and mapped category in our snapshot. And the last one, as you can see, is dirty. For the rest of the presentation, we'll only use allocated and resident terms, but I think like, because in some tools you will see this like term used, so I think like it's important to cover it as well. In short, dirty just means modified. So if it's like the part of memory that operation system can't easily discard, which is currently like present in physical memory, because it doesn't exist anywhere else. Well, from the point of view of operation system, not all resident memory is dirty, because well, whenever, for example, you have map files, operation system load part of that map file into memory, but actually. It can discard it at any time because the same data that is loaded into memory exists on disk file or on disk. So, it just considered like a that whenever it's just dirty, it's just like the limit that operation system cannot go below at any case. Well, unless it can be swapped into swap file. To summarize it all, just consider like allocated as like what you have requested, like if you want like a short and simple summary of that. And resident is what is currently physically present in memory. It's kind of like very simplified, but if we focus on this too much, we're probably going to spend the entire day discussing it. And before we jump into like looking at actual snapshot, I want to talk about like what actually allocates memory apart from like your script. So before Memory Profiler 1.0 and Unity 22.3, we mostly showed you only Unity allocations and mono/alt/cpp virtual machine state, like heap. But for Memory Profiler 1.0 and 1.1, and we just wanted to reduce to the minimum the amount of like memory, like the difference between what you see in Memory Profiler and what you can see in any native operation system like profiling tools. I don't know, or like Task Manager, Activity Monitor, or any profiling tool, well, of your choice. So that if you open like Task Manager, you will see the same amount of memory, roughly, because there's kind of like different ways to measure what the total what total memory is, but they will be quite close. So for that, we need to show you all allocations, not just what Unity makes directly or like UDIT makes directly. All allocations associated with your application. And most importantly, when we talk about all of memory, well, obviously you don't want just learn how much, because, well, it kind of like gives the information, but it's not very actionable. But as well, you want to know who allocated it, which allows you to act on it. And talking about like allocation sources, the first one I want to talk about is shared libraries. Your application's code relies on quite a lot of external shared libraries. These shared libraries might in turn rely on other libraries and so on. All of them contribute to your total allocated memory and obviously your application's memory footprint. Well, just a simple example, you on Windows use DirectX, which uses some kind of like graphics drivers, and drivers use system libraries and so on. So all these libraries will be loaded. All of them, well, will be mapped into your application's address space. They will use some kind of like some amount of physical memory, as well as they will going to do allocations to maintain their own states. The next important one is like runtime environment. It's not present on all like platforms, but in some cases, operation system might need a special virtual machine for your application to run. Most common example, or most well-known, would be Android runtime. On consoles, we can kind of like think about SDK libraries that provide the operation system-like environment as this kind of like runtime as well, because they do allocations as well. Another big source could be drivers, operation system drivers for different devices like video, network, audio. Drivers might allocate in direct reaction to your actions, like you requested texture, and it allocates texture for you and does allocations for that. Or maybe just like to maintain an internal state, like buffer to communicate with a device, for example. And the last important source, like apart from like Unity and like the previously known, let's call it that, is object that operation system needs to maintain its context. It's like threads, stacks, heaps, and so on. All of these contribute to your total allocated memory of your application, and obviously need to be accounted, and might be quite significant. We will talk about this in detail in Untrack, but I will just give you an example of my recent case. People ask me to investigate why we have like almost like 2 GB of untracked memory on Linux empty project. Well, Unity by default on machines with like creates almost like a 2.5, let's go like 2.5 thread per core, and on machine of like with lattice like Threadripper, you can easily get to a state of like 200 or 300 threads by default. And unfortunately, Linux request around like 8 megabytes stack for each thread. So you can multiply, and you will get just almost 2 gigabytes allocated just for maintaining thread stacks. So this information is quite important and can kind of raise a lot of questions why so much memory is being used. So let's move to the practical part, and let's take a look at actual memory snapshot. As we move to that part, as I mentioned, I took snapshot from Android game. For the talk, we assume that the game targets device with 2 gigabytes of memory. So they just set kind of like environment and expectations. And let's kind of like think that we open that snapshot and look at the summary page, as you can see it in here. And yeah, as I mentioned, like we agree that device will have 2 gigabytes of memory, and immediately we see like in allocated memory distribution, the total allocated memory is surprisingly 2.2 gigabytes. And yeah, as I mentioned, like we just agreed our device have just 2 gigabytes. So are we in trouble or not? Like it does look like our game is not going to run on our target device. And surprisingly, like it's quite a small game, but we can see that Android Runtime and Executables and Maps taking surprisingly a lot of memory, like 60 to 70%. And you might think, like, okay, that's my most, like, that's like the trouble is. But the question is, if we take a look at the like section above, memory usage on device, and it doesn't look like where we need so much space. So just why is it like, I mean, it does say like that the amount of physical memory being used is just, well, around 500 megabytes, which is well within the limit that we set for ourselves. So the question now is just like, are we in trouble or not? Because, well, it does look like a bit confusing. So let's take a look at all the categories and, well, see what's in there to understand, are we actually in trouble or not? So we start with Android, like from the biggest one, Android Runtime. And Android Runtime is just like a virtual machine that which runs Java bytecode on Android platforms. It's kind of like similar to Unity, like Mono or LCPP virtual machine. It manages heaps, have garbage collector, compiles bytecode in native code, and so on. All Android applications, well, apart from system one probably, all Android, like typical Android applications, like share Android runtime heap, and because applications use it, we need to show it in memory profiler just to see to show you the full picture. Because, well, applications might be different. Some might be quite lean on the Java part, but some can create objects in Java Kotlin, allocate in the heap, in the Java heap, or use third-party SDKs and toolkits, which do have quite significant Java part. Unfortunately, if you read about Android runtime, you actually don't have any control over its size. It's being defined by your phone vendor, and the size is being set at initialization of operation system, so it kind of like allocates at your phone start and doesn't change after. So does it mean that Android runtime contribute a lot to your memory consumption? But if you look at the resident memory size, it's just 4 megabytes. So if only like just tiny fraction of it, why do we even include this? Well, as I mentioned, all applications are different. Like first of all, like all applications are different, and you might have a bigger chunk in here, and then in this case, you will need to analyze. The second one, is that, well, we just agreed we're going to show you all allocations which are associated with your application, and Android Runtime is definitely associated in your application because it's being mapped in your application's address space. So, if it's like that, does it mean like we don't need to analyze it? The answer is no, but it depends. So in this particular case, you need to focus on resident size rather than allocated size because allocated size doesn't give you any information. And in our application's case, it's just 4 megabyte, and probably we won't be able to reduce it any further and compare it to the rest of 400. It does seems like a pretty small size, so it does seems like it's not a problem for our application. Well, if it's not a problem, let's take a look at the next big category, executables and mapped. We already had executables and DLLs in previous versions of Memory Profiler. However, well, you need to understand the difference because before Unity 22.3 and Memory Profiler 1.0, it actually was kind of fake because previously it showed you just a collection of binary files in your build folder, which obviously doesn't map to what your memory consumption is. And we upgraded it, so starting from Unity 22.3, it actually shows you in the same way as operation system sees it. So now it shows you all executable files, all shared libraries, all mapped files that contribute to your application's memory footprint as seen by operation system. So you can see them all listed in here. For example, yeah, if we look at it, yeah, at the top it will be OpenGL library, some frameworks, and the application executable. When you analyze this section, because this is like when we talked about Dodi, this is the section that kind of like affected by this the most, because if these files are just being loaded, we don't modify them, so the operating system always have a copy of it. So because whenever you map a file, operating system just makes like the part which is being accessed, it being brought into physical memory. And because it's not dirty, and it's not modified, obviously, because that the data on memory, data in memory can be discarded at any moment. And well, that means that despite the fact that all of these contributes to your resident memory, it actually might not contribute to your out of memory issue directly, but it will contribute to your performance. Because as soon as you get to the point when you are close to well, maximum memory footprint that your operation system sets, operation system will start to discard stuff. But if you keep on accessing the file, it means like it will need to reload them and discard something else. So you will start experiencing performance regressions well before you hit the out of memory issue, and you need to look for it. Well, and for simplicity, we haven't included dirty into memory profiler because I think it just adds too much. But in most of the cases, resident is always bigger than dirty, and much better indicator of your application's healthy memory needs. So this again means that resident size, especially in particular in this case, is more important for analysis, well, as well as for Android runtime compared to allocated, as is the part that operation system consider important to keep in memory. So, yeah, if we look at the again at the list for our application, it doesn't look like anything in particular is like super large and well, probably you can get rid of OpenGL if you need OpenGL. So yeah, I mean, I did like an extra profiling just thinking about like what can be reduced. But in here, most of the time, apart from looking for SDKs tool like that you kind of like haven't expected to see, or too large Unity binary, which usually is a sign that you probably abuse generics without CPP. These kind of things, which are particular of interest in this category. But generally, just assume if you see too much resident memory in this particular category, it might need additional investigation. So the next big one is graphics. Well, if previous categories kind of like felt confusing because, well, what you need to look at, like some of them are pre-allocated for you by person systems, so this one is actually the most confusing, so stay focused. First of all, just remember, memory profiler shows you only system memory information. So it never shows you what's on your GPU, which is kind of like, well, at this point you might feel like, well, it's strange because you have graphics. What about that? And that's the thing. Graphic isn't about GPU local memory. It's about what's actually in your system memory. And it's not about this infamous read-write enabled flag. So just, again, a bit of the theory. Why is that? There are two common memory architecture when it comes to platforms we work on. The first one is UMA. It's Unified Memory Access. So all graphics allocations are in system memory. So GPU shares memory with CPU, and it's called graphics stolen memory when GPU just steals memory from CPU. And the second one, obviously, non-UMA, when you have usually dedicated graphics card, which have dedicated memory. So, I mean, it's kind of like obvious with UMA, because we allocate from system memory, GPU shares memory with CPU, so, and it's all in system memory, no questions. So why then we show it for non-UMA platforms as well? The thing is when we have GPU with dedicated memory, usually on desktops, operation system needs to share that local memory between multiple applications. And the way it's designed so that at any given moment, operation system like reserves right to evict any resources out of GPU at any given moment because it needs it for another application. And it's driver's responsibility to make sure that all the resources that your application needs will be maintained in a valid state. And what drivers do, they allocate memory for any resources that you use, which is being called like local baking store if you profile on Windows. I don't remember how it's called on macOS, but the fact is that drivers maintain kind of like shadow copy of your resources for cases when it needs to, or like it's being asked to evict all resources application associated with your application. So just keep in mind that even if it's not UMA, your application will receive these allocations, and they will be associated with your application and count towards your total allocated memory. And another kind of like nail in this is just, it's all kind of like hidden. So it's somewhere well within kernel, and we can see these allocations. So if we can see these allocations, well, we can track them, why and how we are showing them. We actually kind of like fake them, and that's why we now write, just to be absolutely clear, we write estimated. So we take information about resources we know has been allocated, like texture, width, height, bits per pixel, any additional information about format, and we estimate how much they should be, like how much we think they will be taken, how much memory they will be taking. So that altogether allows us to estimate how much memory has been allocated by graphics resources. And just to make sure that we not creating any additional memory, whenever we do estimation, we subtract it from untracked, and that's why untracked have this asterisk next to it, just to indicate that we just made some magical compensation just to be able to show you this graphics memory. And because we estimated, we don't have any information about whereabouts of these resources in memory. And because we don't have information about their whereabouts, we can say how much of them are actually resident. So if you switch to resident view in memory profiler, to be absolutely truthful with you, we will just show you NA, just to indicate we don't know how much of net memory is actually resident. And all of that memory will be counted towards untracked, because we kind of like, operation system reports you that this memory has been allocated, how much memory is actually resident, but we don't know who actually allocated it. So it doesn't spoil like total allocated, but unfortunately makes it like less informative. On the positive side, with latest Unity, we spent quite a lot of time to improve estimation code. So now it takes into account, well, I think like everything. Well, 3D texture, MSA, memoryless render targets, compressed textures, all of them now needs to be, I assume, like I hope, estimated correctly. So even though they're still estimates, this information is quite useful if you need to estimate how much memory is being consumed by graphics resources. The next one is native. And native is so much easier compared to all the previous ones. So it's actually everything that Unity allocates for you outside of, well, not managed here, but inside of it. All Unity allocations, because we have like a memory manager would perform all allocation management inside of Unity. All allocations are labeled and pooled. So whenever you do allocation, we kind of like allocate inside pool, which if we don't have enough space inside pool, we allocate another chunk and allocate inside of that chunk. That's why you can see reserved, because, well, we allocate chunk, we allocate inside of this chunk. So some of that space, despite the fact that the operation system thinks that it has been allocated, is not being used by anything. So it's being reserved and will be used the next time you allocate something. And as well, like probably you've seen reserved previously on summary view, we moved it in here because in breakdown view now, because now you can get into reserved and see which allocations, which allocators in particular, well, are being not properly used, I would say. And I have to mention that whenever you allocate this particular session, probably as well as like resident, which is directly information about like your memory footprint, allocated is as important because all of these objects are quite often used, and allocated is like a very good indicator of how much resident memory your applications need to function properly. So even if though it's like not 100% resident, expect it might be at any point. And talking about our Android game, well, the only part, like when I analyzed it, which looked suspicious, was reserved, in particular because, well, it's quite large, to be honest. So, as I mentioned, well, now you can just expand it to see what's in there. And as you can see, the biggest offender, log profiler, you won't see it in actual release game. It just means that profiler needs to do allocations to function, and that's what caused this particular allocator to expand. The second biggest is alloc default. This particular probably a bit more troublesome because usually, well, you allocated something that caused Unity memory pool to expand, and then you released it. Theoretically speaking, if you released everything in the chunk will be released. So it's not like monoheap, which never contract. But if you mix together like long-term and short-term allocations, it means like the chances of your memory fragmentations are quite high. So if you have like a 16 megabyte chunk and have like 8-byte allocation inside of it, this chunk will still resides like, you can say like in memory, but being marked as allocated. And it probably won't affect your resident memory size as much. But as you, like I mentioned that anything at any particular time might become resident. As you can see, quite significant part of reserved is actually resident as well. It's just the indication that it was used just a moment before we took the snapshot. We kind of provide information how to customize this. So it's not like completely unactionable, but unfortunately, probably like you need to have deep understanding about how Unity Memory Manager works to do it properly. Well, you can try, like we have documentation page about memory allocator customization, which allows you to do that, and there would be a link at the end. But, well, you can do that, but to be honest, I discourage you from doing that because probably you will do, you might do it, like, make it worse. So the next category is managed. And that's well known, and we talked about it a lot. The managed category shows you all allocations related to mono or LCPP virtual machine. I won't go much deeper into the detail. As I mentioned at the beginning, I think it's pretty well described. So just let's go briefly about like what you can see in here. And the first one is virtual machine. It's any allocations which mono or LCPP makes to maintain its internal state. Resort in this particular case, slightly different from the previous. It just managed heap have sections which are not being used. So anything not being used by managed objects, but inside like managed heap goes into resort. And well, managed objects is just managed objects, like the thing you allocate in C# or we allocate for you. There's interesting bit about this section. As you can see, well, it's not big, but it's 100% resident. Why is that? It's the way Boehm garbage collector works. What it does, it kind of like scans your memory, looking for pointers of objects to make sure that it can mark objects as alive. So it means like it actually touches everything all the time and make sure that all of your managed heap is actually present in physical memory. So keep this in mind. And actually, that's why like maybe like just targeting managed heap is just managed heap is not such a bad strategy because if you like scripts heavy, which many games are, this usually is the biggest offender. Well, not in our case, but still. And if you're interested just in managed objects, I would recommend you to use Unity Objects View because it allows you to just laser focus on just managed objects. And it does provide you a bit of extra functionality to quickly find like duplicates or just look at the view differently. And the last category I want to talk about is untracked. Let's talk about like what are the most common sources of untracked. So why we get this? The first one is, well, as I mentioned at the beginning, thread stacks. In our particular case, it's not that large because, well, Android is not as generous as just Ubuntu probably. So in our case, it's just 8 megabytes, which is pretty healthy. But as I mentioned at the beginning, different platforms does things differently. Sometimes you can see a lot in untracked just because it falls into thread allocation. The next thing is I want to mention third-party plugins and third-party libraries allocation used by third-party libraries used by Unity, which do allocations. Not all libraries provide us functionality to override allocator, and if we can't, unfortunately, allocations go into Untracked as well. But if you use third-party plugins, we now have API which lets third-party plugins to use Unity Memory Manager to kind of let us track these allocations, but not too many plugins actually use it. But so most often, if it just all these plugins use normal allocation functions for C++, like malloc, new, you will see in here it's called heap or add-on libc malloc. It depends on how it was managed through libc or system heaps. But generally speaking, yeah, that's usually the way they look. And well, as we talked about graphics, I mentioned that graphics allocations can be tracked, or well, whenever you have resident memory view, so make sure that you understand that whenever you switch to just resident side, or whenever you allocate it in resident or resident, all your graphics resources will be shown as NA and will go into somewhere in here, most commonly private. Sometimes you have, well, for example, dev Mali in this case. That's Mali GPU, because we're on Android. On iOS, you will see I/O accelerator, because in here we show you different tags. And these tags are coming from operation systems. So some operation system provides you functionality to kind of name allocations and or associate them with certain subsystem. It unfortunately not very actionable, but provide at least some information about what these memory, who could have allocated this memory. So it's last resort. So we haven't found anything in monoheap, Unity allocations, or executables. So let's show you at least something. Maybe because you have much more context about your game, so you might guess what these allocations are. So we talked a lot about quite significant time about Untracked, and well, unfortunately, if all these tags doesn't help you much, what you can do. So the only option you have in this case is just native platform tools. I don't want to go deep into how they work inside. I just want to list them just in case if you decide to use them. So on Windows, it's Windows Performance Recorder, Windows Performance Analyzer. It's slow and not very user-friendly, but allows you to profile user and kernel memory allocations. So you will see graphics allocations as they happen, and it's totally free. On Linux, Intel vTune, and I was mentioned during the previous talk that dot trace actually allows you to profile on vTune and should be working with Unity as well. But everything else I tried is actually crashes or doesn't work with Unity at all. On macOS, iOS, obviously, Xcode instruments, nice instrument and work out of the box. On Android, you have Android Studio. Unfortunately, you need to have rooted phone to get it work properly. So it might work, but most of the time doesn't, unless you have rooted phone. So let me jump into summary because we're quite close to the time limit. First of all, resident memory is the key. Use the new resident memory column for memory footprint analysis, and it's your source of truth about what is in physical memory. It also helps you predict out-of-memory issue because you're in trouble if you're close to 60% of your target device physical memory. It might vary between different platforms, but general rule is that if you're close to that limit, first of all, you will start experiencing performance issues because a first system will start to actively manage what is in physical memory. And secondly, some platforms will just have hard limit about how much memory you can use. Mind the context. As I mentioned, each category needs to be looked at. So there is no a silver bullet. Different categories require different approaches. Sometimes you need to pay attention to resident only and ignore allocated like entirely. Sometimes both are kind of like important. So remember, the moment you touch any object, it becomes resident. And with so much focus on resident, you might wonder why we keep allocated at all. So for example, it kind of works as mental bridge. If you allocated 1 megabyte of memory and you want to see this 1 megabyte in tool of memory profiling tool, just to understand that this is exactly the object you have allocated. And that allows you to kind of like build the mental bridge. Oh, this is the object I allocated, and that's how much actually memory is being taken in physical memory. And obviously, resident memory doesn't work with graphics allocations, and if we want to show graphics allocations, we need to keep allocated as well. And use memory profiler 1.1. It provides more detailed and correct information compared to older versions. You can use it even with older snapshots, so it doesn't require you specifically latest Unity. It just gives you much more information with latest Unity, but you can use better and updated UI even if you are on Unity like 2019 something. And well, as I mentioned, use Unity Objects View if the only thing you are interested in is memory heap, is managed heap. Because in this case, it's much simpler, much more focused, and it will help you with simple cases. These are the links I mentioned. Well, 1.1 package, allocator customization, my blog post about memory footprint, and my colleague post about Unity Objects View and how to inspect object memory. Thank you very much for being present here. And yeah, do we have time for questions?